NASA's interim administrator just admitted their $4.2 billion per launch Artemis program is unsustainable, while SpaceX's original 2017 proposal could do the same mission for $40 million using a single Starship. But here's what most missed. SpaceX designed Starship for full Earth-to-Moon-to-Earth missions before NASA even selected them. Why did NASA ignore this simpler approach? And what's changed that makes it viable now? NASA's interim administrator Sean Duffy recently made a startling admission that should send shockwaves through the space industry. At $4 billion a year launch, you don't have a moon program. But here's what few people realize. SpaceX already solved this exact problem 6 years ago with a revolutionary design that NASA completely overlooked. When Elon Musk unveiled Starship's lunar concept at the 2017 International Astronautical Congress, most dismissed it as typical overpromising. But that original design wasn't just another flashy presentation. It was a fundamentally different engineering approach that could eliminate NASA's biggest headache: the need for two separate transportation systems that must work perfectly together in the vacuum of space. Think of NASA's current Artemis plan like planning a cross-country trip where you drive to the airport, fly to your destination, then switch to a completely different vehicle for the final leg. Every handoff adds complexity, cost, and potential failure points. The Space Launch System and Orion handle Earth to lunar orbit, while Starship's Human Landing System variant manages lunar orbit to surface. Each transition requires precise orbital mechanics, docking procedures, and crew transfers in one of the most hostile environments imaginable. SpaceX's original 2017 proposal was radically different. One vehicle for the entire journey. A single Starship would launch from Earth, refuel in elliptical orbit, fly directly to the moon, land on the surface, and return the crew safely to Earth, complete with atmospheric re-entry and vertical landing. No complex orbital rendezvous. No switching vehicles 240,000 miles from home. No hoping that two completely different systems would integrate flawlessly. The engineering elegance is remarkable when you break down the numbers. Where NASA uses the 322-foot-tall SLS rocket plus a separate Orion spacecraft weighing 26.5 tons, SpaceX proposed doing everything with one 394-foot reusable vehicle capable of carrying over 100 tons to the lunar surface. The payload capacity difference alone is staggering. While SLS can deliver about 27 tons to lunar orbit, Starship's design targets 100 to 150 tons directly to the lunar surface. And here's what's truly noteworthy about the cost revolution. NASA's own Office of Inspector General estimates each SLS launch costs at least $4.2 billion for the first 4 Artemis missions. Add in the Orion spacecraft, and you're looking at approximately $5.2 billion per mission. Meanwhile, Elon Musk has stated Starship launches could eventually cost as little as $2 to $3 million, with realistic commercial pricing likely around $40 million per launch. That means NASA could theoretically get 130 Starship missions for the cost of a single SLS/Orion flight. But the real breakthrough everyone missed in 2017 is thermal protection technology. Returning from lunar orbit generates significantly more heat than low Earth orbit reentry, approximately 11 kilometers per second versus 7.8 kilometers per second for typical ISS returns. This 40% velocity increase creates exponentially higher thermal loads that seemed impossible to manage with reusable heat shields when SpaceX first proposed the concept. Here's what few people realize about SpaceX's quiet revolution. They've been developing their thermal protection system tiles specifically for this lunar return challenge. Laboratory testing has confirmed these advanced tiles can withstand the extreme temperatures associated with lunar re-entry, validating what seemed like science fiction just 6 years ago. The hexagonal tiles use a proprietary silicon carbide material that maintains structural integrity at temperatures exceeding 1,600 degrees Celsius. The propulsion system design reveals another layer of sophisticated engineering that most analyses overlook. While NASA's troubled exploration upper stage relies on 4 RL-10 C3 engines producing 433 kilonewtons of combined thrust, Starship employs 33 Raptor engines generating over 7,500 kilonewtons at sea level. This isn't just about raw power, it's about reliability through redundancy. Lose one engine on the SLS upper stage, and the mission likely fails. Lose several Raptor engines, and Starship can still complete its mission successfully. We'll come back to why this engine-out capability becomes critical for lunar operations. But first, here's what most people overlook about the maintenance revolution that's reshaping the entire space industry. But this is just the beginning. What's really surprising is how this technical approach completely reshapes the economics and politics of lunar exploration in ways NASA never anticipated. NASA finds itself in an unprecedented and politically explosive position. For the first time since Apollo, a commercial company has developed capabilities that not only match, but exceed the agency's own systems, and at a fraction of the cost. This isn't just about rockets, it's about the fundamental business model of space exploration crumbling in real time. Consider the maintenance nightmare NASA refuses to discuss publicly. The current Artemis architecture requires maintaining two completely different vehicle fleets with incompatible systems, supply chains, and operational procedures. SLS components are essentially expendable, manufactured in limited quantities with specialized tooling that takes months to set up for each production run. Each Orion capsule requires extensive refurbishment after ocean splashdown, with saltwater corrosion adding massive complexity and cost to what should be routine maintenance. Starship's approach flips this maintenance model entirely. By returning the same vehicle to Earth after each mission, SpaceX can leverage existing ground infrastructure, technicians, and supply chains for maintenance and refurbishment. Think of it like the difference between maintaining a commercial airliner at a major hub with full facilities versus trying to service it at a remote desert airport with no infrastructure, no parts, and no experienced mechanics. And here's what most people don't realize about the international implications. This maintenance advantage becomes absolutely critical for sustained lunar operations. NASA's current plan essentially abandons expensive hardware after each mission. The SLS is completely expendable, and the Orion capsule splashes down in corrosive ocean water. SpaceX's approach enables the same vehicle to fly multiple missions, with routine maintenance performed using Earth-based infrastructure that already exists. The competitive landscape reveals even deeper problems with NASA's current approach. Blue Origin's New Glenn upper stage, proposed as an alternative to NASA's troubled exploration upper stage, faces a critical design flaw that most analyses completely miss. The combined height of SLS core stage plus New Glenn upper stage would exceed the maximum clearance of Kennedy Space Center's vertical assembly building doors. Accommodating this configuration would require costly and time-consuming modifications to the VAB's structure, potentially adding hundreds of millions in costs and years to the timeline. But there's a detail that changes everything about the competitive dynamics: manufacturing capacity. SpaceX is already producing Starship vehicles at their Starbase facility in Texas, with aggressive plans to scale production to dozens of vehicles per year. NASA's SLS, by contrast, can produce perhaps one vehicle annually at current manufacturing rates, maybe two in an exceptional year. This production difference isn't just about economics. It's about the fundamental ability to sustain any meaningful lunar presence. Meanwhile, China's lunar program continues advancing with a focus on speed and cost-effectiveness that should terrify NASA planners. Their Long March 10 rocket, specifically designed for crewed lunar missions, remains on track for a 2030 human landing. While less capable than either SLS or Starship, China's system is being developed faster and cheaper than NASA's current approach, with a clear focus on national prestige rather than international cooperation. The European Space Agency adds another complex wrinkle to this competitive landscape. They've already delivered European service modules for Artemis 2 and 3, representing significant European investment in NASA's current architecture and hundreds of millions in sunk costs. Abandoning this approach to embrace SpaceX's solution risks damaging NASA's reputation as a reliable international partner, potentially affecting future cooperation on Mars missions and other deep space endeavors, where international support becomes absolutely critical. And here's the detail that most people overlook about propellant economics. NASA's current plan requires launching all propellant from Earth for lunar operations, at a cost of roughly $10,000 per kilogram to lunar orbit. SpaceX's integrated approach enables in-situ resource utilization, using abundant lunar ice to produce methane and oxygen propellants directly on the moon's surface. This capability transforms lunar missions from expensive one-way expeditions to sustainable operations with dramatically lower marginal costs. The regulatory implications create additional pressure that could force NASA's hand sooner than anyone expects. The Federal Aviation Administration currently treats each Starship launch as an experimental flight requiring individual environmental assessments and launch licenses. Scaling to the dozens of flights needed for lunar refueling operations will require fundamental changes to launch licensing frameworks, changes that typically take years to implement, but could be accelerated under political pressure. As we'll see in the next section, these converging pressures create a perfect storm that could force NASA to abandon their current approach entirely, regardless of political considerations or sunk costs. And here's why this changes everything about America's space leadership and the timeline for returning humans to the moon. We're rapidly approaching a moment of truth that could fundamentally reshape human space exploration and America's leadership position in the new space race. The convergence of technical capability, economic pressure, and geopolitical competition is creating a perfect storm that could force NASA's hand much sooner than anyone in Washington expects. Here's the timeline reality that should worry NASA leadership. Hardware for Artemis 2 and 3 is essentially complete, representing billions of dollars in sunk costs and years of development work. The European Space Agency has delivered service modules, contractors have manufactured heat shields, and astronauts are training for missions using the current architecture. But what happens if SpaceX successfully demonstrates end-to-end lunar capability before these expensive missions actually fly? NASA would face the politically explosive situation of launching a $5.2 billion mission using demonstrably inferior and more expensive technology, while a superior solution sits unused at SpaceX's Starbase facility in Texas. The optics would be devastating for an agency already facing criticism about cost overruns and delays, especially if China's lunar program shows continued progress toward their 2030 target. But here's what few people realize about the safety certification challenge that could accelerate or derail this timeline. NASA's human rating requirements for Starship are fundamentally different from anything SpaceX has faced before. The agency will likely require extraordinary reliability demonstration, potentially 100 consecutive successful launches, before approving crewed lunar missions. This isn't arbitrary bureaucracy. It reflects fundamental philosophical differences between NASA and SpaceX approaches to acceptable risk. NASA's safety culture, shaped by the Challenger and Columbia disasters, emphasizes single-point failure tolerance in dedicated abort systems. The current SLS Orion architecture includes a proven launch abort system with a dedicated motor capable of producing over 1.7 million pounds of thrust to pull the crew capsule away from a failing rocket in milliseconds. Starship has no equivalent traditional escape system, instead relying on engine-out capability, rapid unscheduled disassembly protocols, and statistical reliability through rapid iteration and testing. Both safety approaches can work, but they represent fundamentally different engineering cultures and risk tolerances shaped by different historical experiences and institutional pressures. NASA's approach prioritizes absolute reliability for each individual mission. SpaceX's approach embraces controlled risk through rapid development cycles, extensive testing, and statistical reliability across many flights. The regulatory timeline creates another pressure point that could force rapid decision-making. The Federal Aviation Administration currently treats each Starship launch as an experimental flight requiring individual environmental impact assessments, safety reviews, and launch licenses. Scaling to the dozens of flights needed for lunar refueling operations, SpaceX estimates 8 to 16 tanker flights per lunar mission, will demand fundamental changes to launch approval frameworks that typically require years to implement. And here's the detail that makes this timeline collision almost inevitable: in situ resource utilization development. NASA's current lunar architecture launches all propellant from Earth at enormous cost, roughly $10,000 per kilogram to lunar orbit using current systems. SpaceX's integrated approach enables producing methane and oxygen propellants directly from lunar ice deposits, potentially reducing marginal mission costs by orders of magnitude while enabling permanent lunar infrastructure. The manufacturing and operational implications extend far beyond individual lunar missions. SpaceX's Starbase facility represents a fundamentally new model for spacecraft production, more similar to an automotive assembly line than traditional aerospace manufacturing, with its emphasis on handcrafted, individually tested components. This approach could enable lunar missions to scale from occasional expeditions every few years to regular, routine operations with multiple flights per year. But there's something most analyses miss about the long-term strategic implications: Mars compatibility and dual-use development costs. Unlike NASA's moon-specific architecture that can't be adapted for other destinations, Starship's design enables eventual Mars missions using essentially the same basic vehicle, life support systems, and operational infrastructure. This dual-use capability could justify the massive development costs while opening entirely new possibilities for human expansion beyond Earth. The next 18 to 24 months will determine whether this revolutionary approach becomes operational reality or remains an ambitious proposal. SpaceX has scheduled orbital refueling demonstrations for late 2025, with uncrewed lunar landing tests targeting 2026. These demonstrations will either validate their technical claims or reveal fundamental flaws that could delay implementation by years. What we're really witnessing isn't just the development of a new rocket or mission architecture. It's the potential transformation of space exploration from a government-exclusive endeavor requiring massive taxpayer investment to a commercially sustainable industry that could eventually operate with minimal public funding. The implications extend far beyond lunar exploration to asteroid mining, Mars colonization, and humanity's long-term survival as a multiplanetary species. The political and economic pressures are converging to create a decision point that NASA leadership can't avoid much longer. Either embrace this commercial revolution and risk massive disruption to existing programs and international partnerships, or continue with the current expensive approach and risk losing American leadership in space to more agile competitors. Both choices carry enormous risks, but only one offers the potential for sustainable, long-term lunar presence that could secure America's position as the dominant spacefaring nation for decades to come. This is exactly why SpaceX's 2017 proposal wasn't just another rocket. It was a complete reimagining of sustainable space exploration. What this means is we're witnessing the potential birth of a true space economy, not just expensive government expeditions. The biggest insight isn't the $4 billion savings per mission. It's that SpaceX solved the fundamental problem plaguing human spaceflight since Apollo, making space exploration economically sustainable rather than a massive expense voters eventually abandon. When one vehicle handles Earth to Moon to Earth, maintains itself with existing infrastructure, and produces fuel from lunar resources, space becomes a place humans can build permanently, not just visit. This determines whether America leads space exploration or watches China claim the moon while we write $4 billion checks. The next 18 months will show if these claims become reality. SpaceX's 2025 refueling tests could force NASA to restructure Artemis completely. How do you think this plays out? Will NASA embrace commercial revolution or double down on expensive tradition? This is Space Hub. We analyze what really drives the space race. For insights beyond headlines, you know where to find us. The next chapter might be written sooner than expected.